Hi, Roger, you're up.
Hey, Ignacio. Well, thanks. I know we're running a little later. It planned on schedule. So I'm going to give a quick overview of some new environmental action levels for per and polyfluoroalkyl substances, or PFAS, as we call them. And we just posted to our webpage, I think, a few weeks or so ago. I'm actually giving a more detailed presentation to the state risk assessors group in October. I'm not sure if it's open to the general public or anyone, but it probably is. If not, I can set up something separate. So if you're not on our email list and might be interested in that, then send an email to me and I'll make sure you're notified. So Diana already went over some of the sources of PFAS in the environment. I won't review that, but we don't really, as she said, we don't have any manufacturing facilities in Hawaii. The main concerns we're looking at are places where they did firefight training, potentially wastewater treatment plants, although again, we don't have manufacturers pumping their wastewater into these type of plants, so it's lower risk in a lot of places on the mainland. Possibly leachate from landfill. And again, that's fairly well controlled. And then one thing we're looking at is biosolids for wastewater treatment plants and reuse of biosolids for soil amendments and potential uptake into plants and cows eating the plants and people. Of course, the big concern in Hawaii is just impacts to our groundwater resources. Next slide. It's a reference. It's a document we posted on July 20th, public review draft. Again, we welcome any comments, ideas, anything from outside of Hawaii. We talk to people all over the world, as you'll see in this presentation. And also you see the reference for our environmental hazard evaluation guidance, as I call it, the EALs. That's what we're talking about today is just an addendum to that document. And then our technical guidance manual, we talk about site investigations. So we have several recorded webinars on these topics, not one for PFAS yet, on our webinar webpage. Next slide. So Diana mentioned the chemistry of PFAS. It's actually fairly simple when you look at just the chemical structures. It's just a chain of carbon with fluorine attached and something stuck on the end. So we're just going to use the acronyms in this presentation, but the name's actually fairly simple. It's perfluoro. Those are the main one we're worried about. And then the number of carbon atoms like penta, hexa, heptaocta, et cetera, and then the family. So you might have perfluoro hexasulfonic acids, the sulfur, perfluoro hexa carboxylic acids. So it gets complicated and get tongue-tied on the names themselves, so I'll just put in the acronyms. They can get a little bit more complicated than that. Next slide. So there are hundreds of these compounds or thousands of such. The first step in developing action level is to figure out which compounds to focus on. We talked to people in several states. We've been kind of sitting on the side for several years collecting information on this. California likes to talk about the big 8 or big 9. So you see these 9 different compounds listed here, most commonly found associated with firefighting, foam release sites, landfill leachate, or in biosolids and such. And there are several others just noted down at the bottom. The main focus, as Diana mentioned, in the past really 10 or 20 years even, has been on PFOS and PFOA, because that's what we had toxicity factors for. And that was the first question we had, because we're seeing a lot of these other compounds at other sites, but nothing's being done with the data. There's been a general assumption, well, if you take care of your PFOS and you take care of your PFOA, then you're probably taking care of everything else at the same time. So we wanted to look into that more. Next slide. So we finally had a site here in Hawaii. This is the only one I know of with high concentrations of PFAS, at least in groundwater. It's a fire training area at the Maui airport. It's a very low risk. It's not impacting a source of drinking water. It's really high concentrations of PFAS in the groundwater, like tens, hundreds of ppb. Potential discharge to shorelines, we're concerned more about impacts to aquatic habitats, aquatic life. At this site, they just started, but they tested 2 areas, one in the fire training area and then one downgrading a few hundred feet. And one thing that stood out immediately is the difference in the chemical makeup, PFAS makeup of the 2 areas. The upper area near the source area was dominated by PFOS, as you might kind of expect from what we were reading. You also saw the hexasulfonic acids there in orange and your hexacarboxylic acids there in purple and some PFBS. Kind of typical mix, we thought. But in the downgrading area, completely different. There's no PFOS to speak of. It's all the hexacarboxylic acids, the PFBS, and the hexasulfonic acids. So that threw up a flag. One was for these 2 totally separate source areas. So this is one plume somehow, and the concentrations are getting mixed up. And also is it okay just to look at PFOS and PFOA, maybe in the upper area, but definitely not the lower area. There isn't any PFOS there, and there's still really high concentrations. So we need to look at those two. And then we would use this, we need to expand our list of action levels. Next slide. So now we get an idea of what to look for. Then we have to think of what potential environmental concerns we want to focus on. So for soil, it's pretty straightforward. We look at direct exposure, so there are kids playing in the dirt on a daily basis. And also, especially leaching of these PFAS out of soil and impacts to groundwater. You could also be concerned about plant uptake, but this can be highly variable. I don't really know if we'll ever have action levels for this. It depends on the plant species you're looking at and the soil type and such. So we just focus on direct exposure and leaching for now. Contaminated groundwater, we focus, of course, on impacts to drinking water reserves. Also, especially in Hawaii, discharges to aquatic habitats along shorelines, either from contaminated groundwater or from, say, treated wastewater being discharged offshore. Could also be concerned about irrigation of cropland, say with treated wastewater or contaminated groundwater. Again, that's a separate subject we haven't looked into in detail yet, but we're starting to. Next slide. In Hawaii, we break our sites up into 4 different categories for screening levels based on the groundwater utility and also the proximity to surface water body. So these A1, A2 categories, these areas where the underlying groundwater, first encounter groundwater is the source of drinking water. So we'd compare the groundwater data to drinking water based toxicity, based action levels. But we also, when we get close to streams and such, we want to look at aquatic toxicity. And in category B1, B2, this is areas of groundwater. It's not a source of drinking water, but we're still concerned about discharges to the ocean or streams and aquatic toxicity, chronic and acute toxicity. So we have 4 separate groups of soil and groundwater action levels that we have to develop. You'd only see 1 action level for each one of these groups for soil and groundwater, and that would be the lowest action level for for groundwater for drinking water versus aquatic toxicity. And then the soil would reflect leaching or direct exposure, whichever one is lowest. Next slide. So now we have a general idea of what to look for, what our potential concerns are. The next step was to compile physiochemical constants and toxicity factors for PFAS. So the physiochemical constants is actually pretty easy to compile. The US EPA has a great web page, and for every PFAS that we really needed any information about for dozens. ATSDR, we had some additional information. European Chemical Agency has a lot of really good detailed documents on individual PFAS. I think they're quite a bit ahead of the US in this field. And then there's also some additional information in ITRC document on PFAS. Toxicity factors are more of a challenge. US EPA has only published toxicity factors for 4 PFAS, see noted. Really the main focus has been on PFOS and PFOA. We looked at studies done by Michigan, Minnesota, and Texas, among other states, and we're able to compile toxicity factors for another, 4, 5 PFAS. So we're up to 9 PFAS now, instead of just the 2. The problem was we were still missing toxicity factors for a lot of the PFAS that we were seeing at our one firefighting site, and also from talking with people in California and other states about what they were finding. So luckily we found some guidance published by the Netherlands, RIVM group, used in Europe. They're really one of their main research institutes. And they have relative potency factors for 18 PFAS, including the first ones we talked about. So we can calculate, we can develop toxicity factors for another 9 PFAS. And that covered really well the things we were seeing in sites and people were seeing otherwise. So now we can develop action levels for 18 PFAS based on toxicity. Next slide. Aquatic toxicity action level is a lot more challenging. We can only find chronic and acute toxicity factors for 5 PFAS, and one of them from the UN Department of Environmental Protection, just based on assumption for the hexasulfonic acids. This is a big issue. At least these are fairly common. Under our guidance, if we don't have a aquatic toxicity action level for a chemical, then by default, then we'll use the drinking water action level, just so that the chemical doesn't get forgotten. And then if you test groundwater and it's above that action level, then you do additional studies at the site, and you bioassay or something and get additional data on aquatic toxicity. Next slide. So here's an example of the PFAS environmental action levels for PFOS, the more common ones. And you see for groundwater, there's 2 action levels. For drinking water toxicity, it's 40 parts per trillion. and we discussed how we come up with that number. Aquatic toxicity, in this case, is for chronic toxicity. This number is from Australia. It's 130 parts per trillion. So your groundwater, drinking water-based action level is lower, so it trumps aquatic toxicity in this case. In our lookup tables, you just see one number, 40 parts per trillion. So if your groundwater data for PFOS is lower than this, then you're good to go. If it's above it, then you have to see what your specific issues are. PFOS in soil, direct exposure, 0.13 milligrams per kilogram, 130 parts per billion. But look at the leaching-based action level. This is based on the model we use, 2.5 parts per billion. And for all the PFAS we looked at, the leaching-based action level was, order of magnitude even more lower than the direct exposure. So in theory, that's your main concern. Next step, next slide. So I'm not going to go over these. These are the environmental action levels in cases for soil and groundwater. The groundwater is a current or potential source of drinking water. See soil and groundwater for these 4 different categories of groundwater utility and distance to surface water bodies. I'm not going to say anything here other than look at all the zeros. All these numbers for groundwater, they're all in the parts per trillion, or they range from a low of 19 parts per trillion up to 40 parts per billion. Soil, all the numbers are less than 1 ppm, and some of even less than 1 ppb. Again, that's basically on leaching. Next slide. So these are the action levels. Soil and groundwater. Groundwater is not a current or potential source of drinking water. And where we had aquatic toxicity action levels, they're much higher than drinking water-based toxicity-based action levels, like you see for PFAS, up to 50,000 micrograms per liter. And the corresponding soil action levels are also much higher. So that's good news for shoreline areas. The screening levels, action levels are going to be higher, but all the numbers you see in red are where we didn't have action levels based on aquatic toxicity. So we temporarily just substitute the drinking water action level. So they're back to being really low. We hope to be able to fill those in the near future. We're working with some other states and the grouping EPA to get better aquatic toxicity action levels. Next slide. So what we've been thinking about now, I've been working with Matt Small and some people in California EPA, Matt's with US EPA Region 9, but how can we group all these PFAS in a way that we can make more sense of them and think about what we need to focus on in the field. And so here we plotted the PFAS based on toxicity and mobility. So on the y-axis here, as you go down toward the bottom, that's increasing toxicity. Mobility, like how leachable is this stuff from soil, KOC, absorption coefficient. As you move back to the left to where it's red, these PFAS becoming increasingly mobile. So in the bottom left-hand corner, that red box there, those are PFAS that would be highly toxic and highly mobile. You really want to be concerned about those, say for groundwater. Nothing in that box for now, but there might be it in the future. In the upper right, the green box, low toxicity, low mobility, less of a problem. So thinking about which PFAS are more like PCBs, they're going to stick around in soil. When you look at the high KOC, low mobility, the yellow box on the right, stuff like PFDODA, PFTRDA. In source areas in the soil, you'd expect those to stick around for a long time. They're not going to move much. They're kind of like PCBs, high toxicity, not mobile. Looking at center column there, these are the ones that start to get more mobile. You have to start worrying more about leaching out of the soil, getting in the groundwater. So just focusing on the highest toxicity PFAS first, things like PFNA, PFHXX, the hexasulfonic acid. They're the first ones that come to mind. They're the most toxic. And at high enough concentrations, it could cause problems leaching in groundwater. They're more toxic than PFOS and PFOA. It kind of throws up a red flag. We maybe need to look at more than just PFOS and PFOA in soil and in groundwater. And then you get to the far left, these are the very high mobility compounds. Luckily, most of the PFAS that are high mobility are much lower toxicity. So you'd expect to see stuff like PFDS, and then PF, the hexacarbolic acid. They're going to leach out of soil the fastest and move away from the source area the fastest. Next slide. So we put together a kind of a hypothetical groundwater plume scenario. This is draft. We're just waving our arms in our cubicles and what we might see in the field, but we do think we see this in the field. So if this is a plume, the groundwater is moving from left to right. In the source area, you'd expect to see the more absorptive compounds like PFOS, or in this case, PFDA and FTCAs and other type of compounds. As the plume starts to migrate away from the site, the more absorptive compounds like PFOS, PFNA, they're going to move, but they move slower. If you can think of like a molecule, say a ping pong ball with Velcro on it, the more absorptive is the more Velcro. they'll move in the groundwater, they keep getting stuck. They don't move very fast. So what you'd expect to see at more the leading edge of the plume, you start to see the PFOA and then the hexasulfonic acids again, PFHXS. They're going to start to move away from the source area faster. And then at the leading edge of the plume, you might expect to see stuff like PFBS and hexacarbolic acids and these other compounds where they're much less sorptive, much more mobile. So you could actually see from the same plume very different concentrations or compositions of PFAS makeup in different parts of the same plume. Next slide. So let's go back to the site we found here in Maui. I think that's what we're seeing here. We probably do have a single plume in the groundwater. In the source area, it's dominated by less mobile compounds, PFOS and such. But when you get in the downgrading area, you're seeing those more mobile PFAS, the hexacarbolic acid, PFBS, and the hexasulfonic acids. So the next slide. Then you have to think in terms of risk. So what's driving risk? Can we only look at PFOS? When the source area, probably so. And in this case, whatever has the greatest percentage, say PFOS, if you clean up down to action levels for that compound, you're going to take care of everything else. It's just the way risk works. But in the downgrading area, if you only focused on the PFOS and cleaned up down to that toxicity factor, if this was drinking water, you still have big problems with your hexasulfonic acid. You could miss that. Next slide. Yes. All right, it's my last slide here. Just in summary, so we generate EALs for 18 PFAS compounds, 4 different site scenarios, soil and groundwater. Really expands a lot of other state and EPA guidance. And we borrowed lots from other states and EPA and other countries. Main things to worry about: impacts to drinking water here. Also, natural construction-related discharge to aquatic habitats. Leaching of soil is a big deal. If you fail the leaching-based action levels, you're probably gonna have to go to some kind of laboratory-based leaching test, SPLP test, or the soil column leaching test, which we're developing guidance on. We haven't looked at bioaccumulation in aquatic organisms yet. They're kind of pending uptake into plants too. We still need to look at a lot. The main point, if you're just looking at PFOS and PFOA, you could be missing some potential risks from other PFAS present. Again, we take any ideas, comments, suggestions. We appreciate those. We hope to publish interim final action levels in the fall, and we'll be updating constantly since then, or continuously after that. So thanks a lot.